Definition of concurrency. Concurrency is a programming concept that refers to the ability of a computer to execute multiple computations or processes simultaneously. In Python, concurrency can be achieved through multiple mechanisms, including threads and asynchronous programming. It allows for more efficient use of CPU resources by performing tasks in parallel or by interleaving the execution of tasks to give the appearance of parallel execution on systems with a single CPU. Concurrency is central to writing efficient and performative applications, especially when dealing with I/O-bound operations or when trying to improve the responsiveness of a program. While the concept does not necessarily imply true parallelism, which is achieved with multiprocessing on multiple CPU cores, it does enable tasks to make progress without waiting for other tasks to complete, which can be crucial in creating high-performance applications that are capable of handling multiple events or user interactions at the same time. Concurrency versus parallelism. Understanding the difference between concurrency and parallelism is fundamental in Python programming, especially when dealing with performance optimization and the efficient use of resources in your applications. Concurrency and parallelism both deal with multiple tasks happening within the same time frame, but they are different concepts. Concurrency is about dealing with lots of things at once, which is like a single person juggling multiple tasks, switching quickly between them to give the appearance of simultaneous progression. Meanwhile, parallelism is about doing lots of things at the same time, akin to having multiple people each performing a task simultaneously. In Python, the global interpreter lock makes true parallelism difficult with threads, leading to a preference for concurrency via threading or asyncio, or multiprocessing for parallel tasks. Use cases for concurrency. Concurrency in Python is a concept that allows multiple tasks to run in an overlapping manner, improving the efficiency of programs, especially when dealing with I/O-bound or high-latency operations. Here's an example using the threading module, which is one of the ways to achieve concurrency in Python. In this code, we create two threads, each targeting the print numbers function. By doing this, the function is executed concurrently in two separate threads. When we start both threads with thread1.start and thread2. They run independently and potentially in parallel, depending on the number of CPU cores and the Python interpreter's capability. The join method ensures that the main program waits for the threads to complete their tasks. This example illustrates a basic use case of concurrency, where tasks are being run concurrently to maximize the use of available computational resources. Challenges of concurrent programming. Race conditions occur when two or more threads can access shared data and they try to change it at the same time. This can lead to inconsistent results depending on the order of operations. In the provided example, two threads are modifying the shared global variable counter. They attempt to increment and decrement it 100,000 times each. Without proper synchronization, running this code could yield different results each time, which demonstrates a race condition. Threads versus processes. In Python, concurrency can be achieved through threading or multiprocessing. Threading allows multiple threads to run in the same process and share memory space, useful for I/O-bound tasks. Multiprocessing, on the other hand, runs each process in its own memory space and is better for CPU-bound tasks. This code demonstrates the basic creation and execution of a thread and a process in Python. We define a function printNumbers, which simply prints numbers from 0 to 4, prefixed by a label. A thread and a process are both created to execute this function. The thread will run concurrently within the main process and may share the same memory with other threads. The process will run independently and have its own memory space. Note that the process must be explicitly joined with p.join, which waits for the process to finish its execution before continuing the main program. Definition and implications of GIL. The global interpreter lock, GIL, is a mutex that allows only one thread to execute Python bytecode at a time. The GIL prevents multiple native threads from executing Python bytecodes simultaneously, which can lead to contention in multi-threaded applications seeking to utilize multiple CPUs for increased performance. The code creates two threads, each of which executes a simple countdown function that decrements a number until it reaches 0. In a multi-core processor without the GL, you might expect this operation to run nearly twice as fast as a single-threaded version, since it could run in parallel on 2 cores. However, because of the GIL, even though there are 2 threads, the Python bytecode executes one at a time, which can result in no significant performance gain, and sometimes even a decrease in performance due to the overhead of thread management. How GIL affects Python concurrency. The Global Interpreter Lock, or GIL, is a mutex that protects access to Python objects, preventing multiple threads from executing Python bytecodes at once in a multi-threaded program. This lock is necessary because Python's memory management is not thread-safe. Let's see how this affects a simple concurrent program using threads. In the code, we define a function countDown and create 2 threads which we expect to run in parallel to decrease the countdown as quickly as possible. However, due to the GIL, the threads will not run in true parallel, but will take turns. This means the overall performance will not significantly improve compared to a single-threaded version. The GL effectively serializes the execution of bytecode, which can lead to performance bottlenecks in CPU-bound applications. This example illustrates how the GIL can affect the concurrency, not allowing Python programs to fully utilize multiple CPU cores in multi-threaded scenarios. Strategies for working with GIL. The Global Interpreter Lock, GIL in Python, is a mutex that protects access to Python objects, preventing multiple threads from executing Python bytecodes at once. This can be a bottleneck in CPU-bound multi-threaded programs. Here, we'll discuss a strategy to sidestep the GIL by using the Multiprocessing module, which allows us to create separate processes, each with its own Python interpreter and thus its own pool. In this example, we define a function, printNumbers, that prints numbers from 0 to 4. We then create 2 processes that execute this function in parallel, each in a separate process. Since each process has its own GIL, they can run concurrently on a multi-core system, circumventing the GIL limitation for CPU-bound tasks. We ensure to start and then join each process, making sure the main program waits for them to complete. GIL and multi-core processors. In Python, the Global Interpreter Lock, or GIL, is a mutex that protects access to Python objects, preventing multiple threads from executing Python bytecodes at once. This lock is necessary because CPython's memory management is not thread-safe. However, the GIL can be a bottleneck in CPU-bound and multi-threaded code when running on a multi-core processor, as it prevents threads from executing in parallel on multiple cores. The code defines a simple counter function and runs it in 2 separate threads. Despite using a multi-core processor and running in 2 threads, because of the GIL, these threads will not truly run in parallel, but will instead take turns. This leads to the program not running substantially faster than if it were single-threaded. The timer captures the wall clock time taken to execute, which will likely show that the benefit of the multi-core capabilities is not leveraged due to the GIL. Introduction to Threading Module. In Python, the threading module provides a way to create and manage threads, which are separate lines of execution within a program. Threading can help improve the performance of I/O-bound programs by allowing multiple operations to run concurrently. This code snippet demonstrates how to create a simple thread in Python using the threading module. We define a function printNumbers, which simply prints numbers from 1 to 5. We then create a thread object by passing the target function to threading.thread and call its start method to begin the thread's execution. Finally, thread.join is called to ensure that the main program waits for the thread to complete before exiting. Creating and starting threads. In Python, the threading module provides a way to create and start threads. A thread runs independently and concurrently with other threads. To create a thread, you instantiate a thread object and pass the target function you want to run in the thread, along with any arguments. Then, you start the thread with the start method. This code imports the threading module and defines a thread function that prints a starting message. In the main block, it creates a thread object, x, targeting thread function with an argument 1. The thread is started with x.start. It then waits for the thread to complete with x.join, ensuring the main program waits for the thread to finish execution before it says all done. Joining threads. In the context of threading, joining refers to the act of pausing the execution of one thread until another thread has completed its execution. By using the join method on a thread, you ensure that the main thread, or any other thread, waits for the specified thread to finish before continuing. This is important when you need to synchronize threads, typically when some threads are performing operations that other threads depend on. In this code, we define a worker function that simulates a task by sleeping for 2 seconds. We then create a thread targeting the worker function and start this thread with t.start. After starting the thread, the main thread prints a message indicating that it is waiting for the worker to finish. We use t.join to wait for the worker thread to complete execution. Only after the worker thread has finished, which we know will take 2 seconds because of the sleep call, does the main thread print the final message and continues its execution. Daemon versus non-daemon threads. In Python, threads can be of 2 types, daemon and non-daemon. Daemon threads are those that run in the background and do not block the program from exiting if they are still running. Non-daemon threads, on the other hand, must complete their execution before the program can exit. The main thread of a Python program is always a non-daemon thread. You can set whether a thread is a daemon or not via the daemon property. In the provided code snippet, a daemon thread is created using the threading module. The background task function, designed to simulate a background task, is executed by the daemon thread. We explicitly set the thread as a daemon by setting daemonthread.daemon equals true. The main part of the program continues executing concurrently with the daemon thread. It starts the daemon thread, then moves on to print messages and sleeps for a shorter duration. Due to the main program's completion, the program terminates without waiting for the daemon thread to finish its sleep, demonstrating the property of daemon threads, which do not prevent the program from exiting. Thread synchronization, locks, RLocks. Thread synchronization is essential when threads interact with shared resources to prevent race conditions. A lock object in Python functions as a mutex, allowing only one thread to acquire it at a time, ensuring atomicity of operations. The code demonstrates the use of a lock for synchronization between 2 threads in Python. Value is a shared resource, and 2 functions, increment and decrement, modify it. Each function is run in a separate thread and uses lock.acquire to ensure that only one thread can access the value variable at a time. This prevents the race condition where both threads simultaneously read and write to the same resource, which can lead to an inconsistent state. After the thread operations are completed, the final value of value is printed, which should consistently be 0 due to synchronized increment and decrement operations. Thread communication, queues. In multi-threaded programs, threads often need to communicate or pass data to one another. This can be complex due to the need for synchronization to avoid race conditions. Python's queue module provides a thread-safe FIFO implementation that can be used for thread communication. Since the queue handles all necessary locking, it makes it easier to safely share data between threads. In the provided code, we have 2 functions named producer and consumer that represent the producer thread and the consumer thread, respectively. The producer places items into a queue, and the consumer takes items out. A queue object created from the queue module is used for this purpose. The producer thread adds items to the queue with the queue.put method, and the consumer thread removes items using queue.get. Once the producer is done, it puts a none object into the queue to signal the consumer to break its loop. The queue.taskDone method in the consumer thread signals that the processing of the item is complete. The main block creates and starts the threads and waits for them to finish using join method. Handling exceptions in threads. Handling exceptions in threads is very similar to handling exceptions in regular single-threaded programs. However, it's important to capture and handle exceptions within the thread's target function, since an unhandled exception will not terminate the main program. We can design the target function to catch its own exceptions and perhaps store them or pass them to the main thread for handling. In the provided code, the thread function is designed to raise an exception, which is then immediately caught by the try-except block. Instead of crashing the whole program, it simply prints the error message. The thread is started with t.start, and when it tries to execute thread function, it raises and catches the value error, handling the exception within the thread's own context. Thread local data. Thread local data is data that is unique to each thread. In Python, the threading module provides a thread local class that allows you to create thread local data structures. Each thread can read and write data to the thread local object without interfering with other threads. This is particularly useful when threads run in parallel and need to maintain their own state. In the provided code snippet, we define myData as a thread local storage using threading.local. We set an attribute x to myData with an initial value of 0. Two functions, print_x and increment_x, interact with myData.x. We then create two threads. Thread 1 calls increment_x, which increments the value of x by 1, and thread 2 calls print_x, which prints the value of x. Since thread 1 runs and joins before thread 2, you would expect thread 2 to print 1. However, myData.x in thread 2 still refers to its own independent instance of x, so it prints 0. This demonstrates that changes in one thread don't affect thread local data in another thread. Introduction to Multiprocessing module. The Multiprocessing module in Python allows us to create processes that can run concurrently. This approach makes use of the multiple CPUs and cores on a computer, resulting in potentially significant performance improvements for CPU-bound tasks. Each process runs independently in its own memory space, avoiding the global interpreter lock (GIL) issue present in threading. This code sample demonstrates creating a new process in Python using the Multiprocessing module. The print numbers function simply prints numbers from 0 to 4. The process class is instantiated with the target function to run in a separate process. The start method is called to begin the process, and join is used to wait for the process to complete before the main program continues or exits. Creating and starting a process. In Python, the multiprocessing module allows you to create and run separate processes. Each process runs in its own Python interpreter and has its own memory space. To create a new process, you instantiate a process object. In the provided code, we import the process class from the multiprocessing module. We define a simple function, myFunction, that prints a message. The if name = main guard is used to ensure that the process creation code only runs when the script is the main program. We create a process object P, specifying the target as the function we want to run in the process. The start method is called on the process object to begin executing the target function in a separate Python interpreter. The join method is then called to wait for the process to complete its task before the main program continues. Process synchronization and shared data. In multiprocessing, process synchronization is crucial when processes share data or resources to avoid conflicts and unexpected results. Python's multiprocessing module provides synchronization primitives like locks, semaphores, conditions, and events, which can be used to synchronize processes. Below is an example using a lock to ensure that only one process can access the shared data at a time. The code creates a shared integer, shared value, and 10 processes that each increment shared value 10,000 times. The add-to-counter function adds to the counter within a context manager that acquires a lock, ensuring that only one process at a time can update the shared data. After all processes have started and finished their execution, join is called. The total count is printed, which should be 100,000. Without the lock, the count could be less because of the race conditions, where processes override each other's updates. Process pools. In Python's multiprocessing module, a pool object allows you to distribute your tasks among multiple processes. Using a process pool, you can map inputs to functions and execute them in parallel. This is useful for parallelizing CPU-intensive tasks. The pool object manages a set of worker processes and a task queue, which distributes tasks to the workers. One common pattern is to use the map method, which is similar to the built-in map function, but executed in parallel. In this code snippet, we import the pool class from the multiprocessing module, but did not fully implement a function. However, the idea is to create a pool of worker processes using pool constructor, and then use the pool to map a function over a sequence of inputs distributed across the processes. This is done by calling pool.map function iterable, where function is the function you want to execute in parallel, and iterable is a sequence of arguments to apply the function to. Process communication, pipes, queues. When using the multiprocessing library in Python, different processes often need to communicate and share data. This is typically done using pipes and queues, which are provided by the multiprocessing module. Pipes allow for two-way communication between two processes, while queues are thread and process safe, allowing multiple producers and consumers. In the provided code, we import process and queue from the multiprocessing module. We define a function worker that takes a queue as an argument. Inside the worker function, we use the put method to insert data into the queue. In the main block, we instantiate a queue, create a process targeting the worker function with the queue as an argument, start the process, wait for it to finish with join, and finally retrieve the data from the queue with get, printing the received message. Managing process state managers. When using multiprocessing, processes don't share memory. Managers provide a way to share data between processes using proxies. A manager object controls a server process, which holds Python objects and allows other processes to manipulate them. One commonly used manager is the manager class, which supports a list, dict, namespace, lock, rlock, semaphore, bounded semaphore, condition, event, barrier, queue, value, and array. This code demonstrates the use of a manager object to create a shared dictionary and list that can be manipulated by multiple processes. The f function updates the shared dictionary and reverses the shared list. In the main block, the manager is created with the with context to ensure it's properly closed. The dict and list under control of the manager are shared between the main process and the child process P. The process P is started, it runs f, and then it joins back. The updates made by f are visible in the main process where the shared dictionary and list are printed. Terminating processes. In multiprocessing, sometimes we may need to terminate a process prematurely, for instance, when a task is taking too long, or when the user triggers a cancel action. Python's multiprocessing library provides the terminate method for process objects to stop a process. In the provided code, a subprocess is spawned to execute the long-running task, which is supposed to sleep for 10 seconds, emulating a long-running task. However, after starting the process, the main program waits only for 2 seconds before it decides to terminate the process. The terminate method is invoked on the process object P, which stops the process. Finally, pjoin is called to ensure that the main program waits for the process termination to complete before moving on. The process terminated message is printed, confirming that the process has indeed been terminated. Multiprocessing best practices. Python's multiprocessing pool is used for parallelizing the execution of a function across multiple input values. It abstracts away the process of spawning processes and offers a simple interface for concurrency. When using pool, keep in mind to minimize the data that is passed to the pool to reduce overhead. In the provided code, we define a simple function compute that squares its input. We use a pool to execute this function across a list of numbers, 1 through 5, in parallel. By using with pool 5 as p, we ensure that the pool is properly closed after use, which is a best practice to prevent resource leaks. The p.map method is analogous to the built-in map function, but executes in parallel. The result is a list of squared values. Mutexes and semaphores. A mutex, short for mutual exclusion, is a synchronization primitive that can be used to protect shared resources in a concurrent environment. In Python, we use the lock class in the threading module to create a mutex. It ensures that only one thread can enter a critical section of code at a time. In this code, we define a counter class with a method increment, which increments the value attribute. To ensure that the increment operation is thread-safe, we use a lock instance called lock. The with statement acquires the lock before entering the block and releases it upon exiting, so only one thread can modify value at a time, preventing race conditions. Conditions. In Python concurrency, a condition is a synchronization primitive that allows threads to wait for certain conditions to be fulfilled before proceeding. It uses a lock that can be tied to a particular state and is useful for implementing scenarios where threads need to wait for resources to become available or for certain conditions to be reached, and can then be notified to continue execution. In the provided code, we define two functions, consumer and producer, which simulate a consumer-producer scenario. The consumer function uses condition.wait to wait for an item to be added to items. This releases the lock and blocks until another thread calls condition.notify or condition.notifyAll, allowing consumer to acquire the lock and continue processing. The producer function adds an item to items and calls condition.notify to wake up a waiting thread. In real scenarios, items should be a shared data structure protected by the condition lock. Events. An event in Python is a synchronization primitive that is used to manage the state, which can be checked by multiple threads. It's a simpler way to communicate between threads. One thread signals an event, and other threads wait for it. In the provided code, we create an event object that is used to block a thread until the event is set. A new thread is started, targeting the waiter function that waits for the event to occur. The main thread simulates some processing and then calls event.set to unblock the waiting thread, signaling that the event has occurred. The waiting thread then resumes, printing a confirmation message and performing any subsequent actions. Barriers. A barrier is a synchronization primitive that is used to synchronize threads. It ensures that a group of threads must stop at a certain point and cannot proceed until all threads have reached this barrier. It is often used where multiple threads need to perform operations up to a certain point before any of them can continue. In the provided code, we import barrier and thread from the threading module. We then set up a barrier for two threads. Two functions, A and B, represent the work done by each thread before and after reaching the barrier. Both threads will print a message before calling barrier.wait, at which point both threads will block until both have called this method. Once both threads have reached the barrier, they are both released to continue execution, and they print a second message indicating they have passed the barrier. Deadlocks and how to avoid them. A deadlock is a state in concurrent programming where two or more threads are blocked forever, each waiting for the other to release a resource. Deadlocks can occur when the following four conditions are true simultaneously: mutual exclusion, hold and wait, no preemption, and circular wait. To avoid deadlocks, these conditions must be broken or prevented. In the provided code snippet, there are two locks and two threads. Each thread is trying to acquire both locks, but they do so in a different order. If thread 1 acquires lock 1 and thread 2 acquires lock 2 simultaneously, a deadlock occurs because each thread will be waiting for the other to release the lock they need next. One common strategy to avoid such a deadlock is to ensure that all threads acquire locks in the same order. This prevents the circular wait condition, breaking one of the necessary conditions for a deadlock to occur. Introduction to Async and Await. Python's Asyncio module is used to write concurrent code using the async await syntax. An async def function is a coroutine that can pause execution with await to wait for I/O-bound tasks without blocking the event loop. Here's a simple example using async and await with asyncio.sleep to simulate an asynchronous task. In this snippet, main is defined as a coroutine using async def. It first prints hello, then awaits asyncio.sleep1, a non-blocking delay of 1 second. During the sleep, control can be given back to the event loop to manage other tasks. After the delay, it prints world. Asyncio.run main is used to run the main coroutine and manage the event loop. Unlike traditional blocking sleep, asyncio.sleep allows the event loop to run other coroutines while waiting. Event loops. An event loop is the core of any asynchronous application in Python, particularly when working with the Asyncio library. It runs in a loop to execute asynchronous tasks, manage their execution, and handle events such as I/O completion or timeouts. An event loop effectively allows the programming to pause and resume tasks at different points, which can make better use of system resources and improve performance for I/O-bound and high-level structured network code. In the provided code, an asynchronous function main is defined. It first prints hello, then awaits asyncio.sleep1, simulating an I/O-bound or time-consuming operation without blocking the event loop. After a 1-second pause, it prints world. The function is executed within the event loop, which is started by calling asyncio.run main. This call creates a new event loop, schedules the main coroutine to run on it, then closes the loop when the coroutine is done. Coroutines. Coroutines in Python are used to write asynchronous code that can perform long-running operations without blocking the execution of your program. They are defined with async def. A coroutine can be suspended and resumed at many points by an event loop, such as asyncio. The code defines a coroutine coroutine that prints a message, suspends execution for 1 second using await asyncio.sleep1, and then prints another message. The coroutine is executed within an async def main function that awaits my coroutine. The event loop is managed manually by getting the default event loop, and run until complete executes main until it is finished. Event loop.close is then called to close the event loop. Future objects. In asynchronous programming, a future object represents a deferred computation that may or may not have completed yet. Futures provide a way to eventually obtain the result of an operation when it's ready. Here's how you can use a future with the Asyncio module in Python. In this example, main is an asynchronous function that gets the current event loop. We then create a future object using that event loop. The setFutureResult coroutine simulates a delayed operation by sleeping for 1 second and then sets the result on the future with future.setResult. The main coroutine schedules setFutureResult as a task and waits for the future to complete with awaitFuture. After the future completes, its result is printed out. Creating and managing tasks. In asynchronous programming, tasks are used to schedule coroutine execution concurrently. When you create a task, you're telling the event loop to run a coroutine and manage its execution. This allows the coroutine to run independently while your program can go on to do other things. The Asyncio module provides APIs for creating and managing tasks. In the provided code, we first import the Asyncio module, which is essential for asynchronous programming in Python. We define an asynchronous function, coroutine, that prints hello, waits for 1 second, simulates an I/O-bound operation using asyncio.sleep, and then prints world. The main function sets up an event loop, creates a task with loop.createTask to schedule my coroutine, and finally, loop.run until complete is called with the task, which starts the event loop and runs until the task is completed. Using async I/O libraries. In Python, asynchronous I/O libraries allow you to perform I/O-bound tasks without blocking the event loop. This is crucial in asynchronous programming to maintain responsiveness and efficiency. A popular example of such a library is AIOHP for asynchronous HTTP requests. In this code snippet, we use AIOTP to fetch content from a URL asynchronously. The fetch URL function is an asynchronous coroutine that takes a URL, creates an HTTP session, and gets the content of the URL. It uses async with to ensure proper resource management of the session and response objects. The main coroutine awaits the fetch URL function to get the content and then prints it. The event loop is then run with run until complete to execute the main coroutine. Running synchronous code in Asyncio event loops. Sometimes, you might need to run blocking synchronous code within the asynchronous framework provided by Asyncio. To prevent the synchronous code from blocking the entire event loop, you can use an executor, such as a thread pool executor, to run the synchronous function in a separate thread. In this code, the Asyncio module's event loop is used to run asynchronous code. The blocking function represents a synchronous, potentially blocking operation. By employing a thread pool executor, the blocking function is offloaded to a separate thread, allowing the event loop to continue running other asynchronous tasks. The loop.runInExecutor method schedules the execution of the blocking function within the thread pool, and await is used to asynchronously wait for its result, integrating it smoothly into the async workflow. Asyncio best practices. The async modifier is used to declare a coroutine, and the await keyword is used within async functions to pause the coroutine, allowing I/O-bound tasks to run efficiently. Let's look at a simple example that demonstrates their usage. In this snippet, main is an asynchronous function. When it gets executed, it first prints hello, then it yields control back to the event loop with await asyncio.sleep1, effectively pausing for 1 second. During this pause, the event loop can run other tasks. After the sleep, world is printed. Introduction to Concurrent.Futures module. The Concurrent.Futures module offers a high-level interface for asynchronously executing callables. It abstracts away the complexities of thread or process management, providing a simple API for running I/O-bound tasks concurrently using threads, thread pool executor, or CPU-bound tasks in parallel using processes, process pool executor. In the code example, we import thread pool executor and define a function loadURL that takes a URL and a timeout and returns the contents of the URL. We create a thread pool executor as a context manager, allowing us to manage worker threads easily. We submit tasks to the executor using executor.submit, which schedules the callable loadURL to be executed with different URLs and a timeout value. Future to URL is a dictionary mapping futures to their associated URLs. We iterate over the futures as they complete, check for exceptions and print return data sizes. This example neatly demonstrates how to use thread pool executor for making concurrent HTTP requests. Thread pool executor. The thread pool executor is a class provided by the Concurrent.Futures module in Python that allows you to execute callables asynchronously using a pool of threads. It simplifies the management of thread creation, execution, and synchronization, offering a high-level interface for asynchronously executing callables. In the provided code, we import thread pool executor from Concurrent.Futures and define a simple function, sum function, that simulates a time-consuming operation. We then create a thread pool executor context manager with 3 workers and submit sum function to be executed with the arguments 2, 3. The main thread continues executing and prints waiting for result, while sum function runs asynchronously in a separate thread. Finally, we wait for the future to complete and get the result, which is printed once available. Process pool executor. The process pool executor is a high-level interface for asynchronously executing callables using a pool of separate processes. It allows parallel execution of tasks in different CPU cores, bypassing the global interpreter lock, GIL, in CPython. This is particularly useful for CPU-bound tasks that can run independently of each other. In the code example, we define a function isPrime to check if a number is prime. We then create a process pool executor with 4 worker processes. Using the executor's map method, we apply the isPrime function to a list of large numbers in parallel. The executor handles creating processes, executing the function concurrently, and collecting results. The use of list around executor.map is to force immediate evaluation, otherwise it would return a generator. After the computation, results hold a list of booleans, indicating whether each number in the input list is a prime. Submitting and managing futures. The Concurrent.Futures module provides a high-level interface for asynchronously executing callables. The primary mechanism for launching parallel tasks is a future, an object that signifies a not yet completed computation. The thread pool executor and process pool executor classes within this module manage a pool of threads or processes and accept tasks to be executed asynchronously. In this code, a thread pool executor is instantiated, allowing up to 2 threads to run simultaneously. 2 tasks are submitted, each of which simply sleeps for a given number of seconds and then returns a result. The submit method schedules the task function to be executed and returns a future object. This object can be used to query the status of the task or wait for its result using the result method. The with context ensures the threads are managed efficiently, automatically joining them when the context block is exited. Scheduling individual and repeating tasks. To schedule individual tasks concurrently, we use thread pool executor or process pool executor from the Concurrent.Futures module. Here's an example using thread pool executor to execute a task that prints a message after a delay. In the code snippet, the print after delay function takes a message and a delay parameter. The thread pool executor is used to run this function in a separate thread. The submit method schedules the task and returns a future object, which represents the execution of the task. The main thread continues to execute and prints a message immediately, while the scheduled task runs concurrently and prints the message after the delay has passed. Handling completed futures. When working with Concurrent.Futures, you often submit several tasks to an executor and need a way to handle them as they complete. The Concurrent.Futures module provides a few methods to do so, such as completed, which returns an iterator that yields futures as they finish executing. The asCompleted function is used after submitting tasks to a thread pool executor. It returns an iterator that yields futures as they are completed, allowing you to handle the results asynchronously. This can be more efficient than waiting for all futures to complete using executor.wait, because you can start processing results as soon as any future is done, without waiting for the rest. Performance considerations. It is important to understand the performance aspects of using Concurrent.Futures. The key factors include the overhead of managing threads or processes, the nature of the tasks, I/O bound versus CPU bound, and the GIL, global interpreter lock, when using thread pool executor in CPython. The code snippet showcases the usage of thread pool executor to run a CPU-bound function, concurrently on multiple inputs. The thread pool is created with 4 workers, and the CPU-bound function is executed 16 times with different inputs. Due to the GIL, using threads for CPU-bound tasks may not provide a performance boost, as threads might not execute truly concurrently. The time.sleep1 call is used to simulate a CPU-bound task, but in a real-world scenario, this would be a computation-intensive operation. The total execution time is printed at the end to evaluate performance. Actor model and concurrency. The actor model is a conceptual model to deal with concurrent computation. It treats actors as the universal primitives of concurrent computation. In this model, an actor encapsulates state and behavior, interacts with other actors by sending and receiving messages. Actors can modify their own state, create more actors, and send messages to others. This approach avoids many concurrency issues by avoiding shared state and using message passing. In the provided code, we use Thespian, a Python library for the actor model. First, we define simple actor that inherits from actor. It overrides receive message to print any received message. An actor system is created using multiproc TCP base, which represents a system capable of sending and receiving messages to actors. We create an instance of simple actor and send a message to it using tell. Finally, shutdown is called on the actor system to clean up any resources. Reactive programming and concurrency. Reactive programming is a paradigm centered around data flows and the propagation of change. It enables developers to build non-blocking, event-driven applications that can easily react to changes over time. This approach fits perfectly with concurrency, where multiple events can happen independently and simultaneously. In Python, one may use libraries like RxPy, reactive extensions for Python, to implement reactive programming concepts. In the provided code, we're using RxPy to demonstrate basic reactive programming. The observeNumbers function creates an observable sequence of numbers from 1 to 5. Using the pipe method, we chain a series of operations. Map multiplies each number by 2, and filter allows only even numbers to pass through. The subscribe method defines what to do with each item, on next, what to do if there's an error, on error, and what to do when the sequence is completed, on completed. The output would display the processed even numbers and completed at the end. Implementing MapReduce pattern. The MapReduce pattern is a programming model for processing large datasets with a parallel, distributed algorithm on a cluster. A MapReduce job usually splits the input data into independent chunks, which are processed by the map tasks in a completely parallel manner. The framework sorts the outputs of the maps, which are then input to the reduce tasks. Python's multiprocessing module can be used to implement a simple version of this pattern. In the code snippet provided, map function is a placeholder for the function that will process each value in parallel. Similarly, reduce function combines all the results returned by the map function. The pool object from the multiprocessing module creates a pool of worker processes. Using pool.map, we distribute the data across the worker processes to apply the map function. Once the map step is complete, reduce function is used to combine all these intermediate results into a single output. Lastly, the result is printed out to the console. This code highlights the main structure of a MapReduce operation using Python's multiprocessing capabilities. Work stealing and load balancing. Work stealing is a scheduling strategy for distributed systems where tasks are dynamically redistributed among multiple workers to achieve load balancing. In Python, this can be implemented using the Concurrent.futures module, which provides a high-level interface for asynchronously executing callables. The thread pool executor and process pool executor internally use work stealing to balance the load across threads or processes. The provided code demonstrates a simple use case of the thread pool executor for load balancing. A pool of 4 workers, threads, is created, and 8 tasks are submitted for execution. As some tasks may complete earlier than others, the thread pool executor redistributes the work so idle threads can steal work from the busiest ones, balancing the overall workload. This is handled internally, and hence the work stealing happens transparently from the developer's perspective. Concurrent data structures, queues, stacks, etc. In concurrent programming, it's important to use data structures that are safe to modify across multiple threads or processes. Python's queue module provides thread-safe queues, which are especially useful for thread communication and data sharing. Here's an example of using a queue in a producer-consumer scenario. The provided code demonstrates a basic producer-consumer pattern using queue.queue. The producer function generates items and inserts them into the queue using put, while the consumer function retrieves these items with get and processes them. The call to task done signalizes that a task has been completed, and queue.join blocks until all items in the queue have been processed. This example ensures that data is safely exchanged between threads without the need for explicit locks, thanks to the thread-safe nature of queue. Debugging threaded applications. Debugging multi-threaded applications can be complex due to the non-deterministic nature of threading, where threads can interleave in unpredictable ways. Python offers various tools to aid in debugging threaded applications, such as using the threading module's built-in logging. Debugging multiprocessing applications. Debugging multiprocessing applications in Python can be challenging due to the complexities of concurrent execution and inter-process communication. Effective debugging requires understanding the tools and techniques that can help pinpoint the source of issues. Unlike single-threaded applications, in multiprocessing, processes operate independently and can run on separate CPUs or cores. Debugging issues like deadlocks, race conditions, or state inconsistencies often necessitates different strategies, such as logging, using debuggers that support multiprocessing, or employing synchronization primitives to coordinate process actions. Techniques for debugging might involve careful inspection of the code, strategic placement of logging statements, or using third-party tools like multiprocessing logging for better log handling. Debugging async applications. Debugging asynchronous applications in Python can be challenging due to the concurrent nature of its execution. However, Python provides various tools and functionalities that can help identify and fix issues within async code. Let's consider a simple async application using the Asyncio library where we want to debug an issue. In the provided code snippet, we defined an async application with 2 simple coroutine functions, fetchData and printer. The main coroutine is the entry point for our asynchronous program, where we schedule both fetchData and printer to run concurrently using asyncio.createTask. To debug this application, you could use logging or print statements, set breakpoints in an IDE that supports async debugging, or utilize the PDB module, Python's debugger, in async mode by calling pdb.setTrace. Additionally, Python 3.7 introduced the asyncio.run high-level API to conveniently run the main coroutine and automatically manage the event loop, making debugging a bit simpler. Profiling concurrent applications. Profiling is crucial for identifying bottlenecks in concurrent applications. Python's cProfile module can be used to gather data on function call frequency and duration, which is helpful for both parallel and asynchronous code. However, when using concurrency frameworks like Asyncio, multiprocessing, or threading, interpreting the results can be more complex due to the interleaved nature of execution. The provided code snippet starts by importing the needed modules for profiling, cProfile, pstats, and Asyncio for asynchronous concurrency. In Do Some Work, an I/O-bound asynchronous task is simulated with asyncio.sleep. The main function uses asyncio.gather to run multiple instances of Do Some Work concurrently. When the script is executed, the cProfile.profile object is initiated, enabled before the asynchronous event loop starts with asyncio.run main, and disabled right after the event loop completes. The results are then sorted and printed. Notably, because of the asynchronous nature of the tasks, await calls are not clocked as CPU time, but rather as blocking I/O, which influences how time spent is reported by the profiler. Detecting race conditions and deadlocks. A race condition occurs when two or more threads can access shared data and they try to change it at the same time. If you suspect a race condition in your program, a simple way of detecting it is by introducing delays at critical points in the code. Then, by running the program multiple times, you can see if the output varies, which is a sign of a race condition. The provided code showcases a typical race condition scenario. We have a global variable, shared data, that both threads try to increment. The increment function does not protect against concurrent access, and thus can result in an incorrect value for shared data when both threads are executed simultaneously. On the other hand, safe increment uses a lock to ensure only one thread can modify shared data at a time, preventing race conditions. Understanding the cost of context switches. When a program is running concurrently, the operating system may switch between different threads or processes. This operation is known as a context switch. Context switches are not free and involve overhead affecting the performance of an application, especially when there are many threads or processes. The following Python code snippet uses the time module to measure the time taken for performing context switches by repeatedly switching between Python threads. The code creates 10,000 threads, each running a function that does nothing, do nothing. It starts each thread and then waits for all of them to complete, using t.join. The time before starting the threads and after waiting for all threads to complete is measured to calculate the total time spent. This includes the time taken by context switches to execute all threads. As the do-nothing function is trivial, the measured time reflects the overhead caused primarily by context switches. The output will show how much time was consumed by context switching alone, highlighting the potential performance impact in a concurrent application. When to choose threads, processes, or async. Python provides several options for running code concurrently. Choosing between threading, multiprocessing, or asynchronous, async programming models depends on the nature of the tasks at hand and the environment in which the Python code is running. Threads should be used for I/O-bound tasks that spend time waiting for I/O operations to complete, such as reading or writing to a file, making network requests. Threads can be implemented using the threading module. On the other hand, processes should be chosen for CPU-bound tasks that require heavy computation and could benefit from multiple CPU cores. They can be managed with the multiprocessing module. Async is preferable when you have many I/O-bound tasks that need to execute concurrently with minimal overhead and without necessarily implementing thread pool management. Async can be implemented using Asyncio. The global interpreter lock in CPython, the default Python interpreter, prevents true parallel execution in a single process, which is a factor for preferring processes over threads for CPU-bound tasks. Scaling applications with concurrency. Concurrency can be leveraged in Python to scale applications, allowing them to handle more work simultaneously. This is accomplished using threads, async I/O, or multiprocessing. Here we'll use the Concurrent.Futures module, which abstracts away much of the complexity involved in directly managing threads or processes. The Concurrent.Futures module provides a high-level interface for asynchronously executing callables. The thread pool executor is used to create a thread pool to execute calls asynchronously. Calls to submit return future objects, which can be queried for status or result, providing a way to execute and manage tasks concurrently. This is ideal for I/O-bound tasks or when you wish to run code in parallel on a multi-core system. By offloading tasks to different threads, a Python application can achieve a higher level of concurrency, resulting in better scalability and responsiveness. Benchmarks and performance testing. Benchmarking in the context of concurrency involves timing how long it takes to execute a piece of code or a function. This is essential in understanding the performance gain, if any, when employing concurrent execution, like using threads or processes. Python provides the time module, which includes the time.perfCounter function, a high-resolution timer that's well suited for benchmarking purposes. In this code, we define a simple CPU-bound task that just counts down from a large number. We then use time.perfCounter to get a high-resolution timestamp before and after running the task. By subtracting the start time from the end time, we get the time taken to complete the task. This value helps in understanding how long a task takes to run, which is critical for making informed decisions about where and how to use concurrency. Resource contention and optimization. In concurrent programming, resource contention occurs when multiple threads or processes try to access the same resource concurrently, leading to potential bottlenecks or race conditions. Optimization involves ensuring that the resources are used efficiently without causing contention or unnecessary overheads. The provided code snippet demonstrates a simple approach to avoid resource contention when incrementing a shared global variable. A lock is employed to ensure that only one thread can modify the value at any given time. Each thread runs the increment value function, which increments the global value variable while ensuring that no other thread can access the variable simultaneously through the use of the with lock statement. This prevents race conditions, ensuring the final output is consistent and correct according to the number of increments performed by the threads. Unit testing approaches. Testing concurrent applications comes with challenges due to the nature of unpredictability in timing and order of operations. Careful design of tests can isolate behaviors and allow for deterministic outcomes, making tests reliable and repeatable. We use synchronization features such as locks, events, or semaphores to gain control over the execution flow and ensure that race conditions or deadlocks can be checked in a test environment. In this code, we're using Python's unit test framework to write a test case for a function that should work correctly when accessed by multiple threads concurrently. Our test thread safety, initializes a shared resource, starts multiple threads that run some concurrent function with this shared resource, and then waits for all threads to complete with join. After thread's completion, it checks a specific condition on the shared resource to ensure the concurrent function did not cause a race condition, data corruption, or any other thread-related issue. The key elements here are the setup to simulate concurrency and the assertions to verify thread-safe behavior. Mocking asynchronous functions. When testing asynchronous code in Python, one often needs to isolate parts of the system and simulate asynchronous behavior of dependencies without executing the actual I/O operations. This is where mocking async functions becomes important. The built-in unittest.mock module can be used to replace parts of your system under test with mock objects and make assertions about how they are used. In this example, unittest.mock.asyncmock is used, which is a helper class designed to mimic async functions. The myAsync func simulates an asynchronous operation that would normally take time to execute, such as I/O operations. In the test myAsync func, we replace the real myAsync func with a mock using mocker.patch. We specify new callable use async mock to indicate that we want to replace it with an async version of a mock. The return value is set to mocked result, so when the myAsync func is called within the test, it immediately returns the mocked result without any delay. The assertion then checks if the result obtained from the myAsync func is the same as the mocked result we defined. Integration testing for race conditions. Integration testing for race conditions involves checking that your application behaves correctly under concurrent operations. Race conditions occur when two or more threads or processes access shared data and try to change it at the same time, leading to unreliable and unpredictable behavior. To test for race conditions, we create tests that intentionally run concurrent operations to try and trigger these undesirable effects. The code above attempts to simulate a race condition by incrementing and decrementing a shared resource, a simple integer, concurrently without any synchronization mechanisms in place. Two threads are started. One increments the shared resource by 1 for 1,000 times, and the other decrements it by the same amount. Ideally, if no race conditions occurred, the final value of the shared resource should be 0. However, since the shared resource is being accessed concurrently without locks, you would most likely end up with a different value, revealing a race condition. In a real-world scenario, unit tests would be equipped with assertions to check for expected behavior, and appropriate locking mechanisms would be employed to prevent race conditions. Stress testing concurrent applications. Stress testing aims to evaluate the performance and stability of an application under extreme conditions. For concurrent applications, this often involves simulating many users or high loads to ensure the application can handle real-world demands without crashing or experiencing unacceptable latency. The provided code snippet demonstrates a simple stress test using Python's concurrent.futures.threadpool executor. The test sends 100 concurrent GET requests to a specified URL and checks if all the requests were successful by validating the HTTP status code. By adjusting the number of concurrent requests and target URL, one can customize the stress test to fit the application's requirements. Packaging applications for deployment. When you're ready to deploy a concurrent application written in Python, it's important to package it in a way that makes it easy to install and run on other systems. One common approach is to use setup tools along with a setup.py script that describes your package and its dependencies. The provided code is a basic setup.py script for a hypothetical concurrent application called myConcurrentApp. This script uses setup tools to define the package name, version, and locate all the packages in the directory for inclusion in the distribution. The install requires list specifies external dependencies needed to run the application, requests, and AIO HTTP. The entry points parameter creates an executable command line tool named runMyApp that invokes the main function within the main module of myConcurrentApp. Users can install the application using pip and run it directly from the command line. Containerization and microservices. Containerization is a lightweight alternative to full machine virtualization that involves encapsulating an application in a container with its own operating environment. This approach enables you to run many containers simultaneously on a given host. Microservices is an architectural style that structures an application as a collection of loosely coupled services, which implement business capabilities. Docker is a popular platform for containerization. Below is an example of defining a Python application with Flask in a Docker container. The code above is a simple Flask application that can be containerized using Docker. To deploy this application, you would need to create a Docker file that specifies the Python environment, installs Flask, and defines the command to run the application. When run in a container, this ensures that the app has everything it needs to run independently of other applications with predictable behavior, because it's insulated from the host system and other containers. Monitoring and logging. Monitoring and logging are critical for understanding the behavior of concurrent applications. They provide insight into the application's performance and potential bottlenecks, and are essential for diagnosing issues that can occur due to race conditions, deadlocks, or other concurrency-related problems. The code initializes logging with a basic configuration that includes the thread name and a message format. It defines a simple task that logs its progress and then squares a provided number. Using a thread pool executor, the code submits tasks to the executor and logs the output once each task is completed. The asCompleted function allows iteration over the futures as they complete, regardless of the order they were started. Handling failures and automatic restarts. In concurrent applications, handling failures and ensuring that the system can recover is crucial. Python provides mechanisms to catch exceptions raised by tasks and restart them if necessary. Below is an example using concurrent.futures.threadpool executor that automatically restarts tasks after a failure. The code uses threadpool executor from concurrent.futures to run multiple tasks concurrently. The function task is designed to raise an exception when the input is 2. The futures dictionary maps future objects to their corresponding task identifiers. The while loop continues to process the futures until all are completed. The for loop iterates over each future as it is completed. When a task raises an exception, it's caught, output to the console, and the task is resubmitted to the pool for execution. Del futures future removes the reference to the completed or failed future before the next iteration.